Last talk of this session will be given by Sanjib Sabhapandit from Ramanujan Research Institute. He will be talking on novel features of direction reversing active Brownian motion. Over to you, sir.
Okay. So I'd like to thank Ranjini and Mahesh for inviting me, but more for also putting together this very nice workshop. I think I guess students, yes.
Positive ion, Santra?
It's a positive ion. It is a positive ion, very positive. Yeah. So yeah. So I hope students have still some energy after this is the third week, I guess. Yeah. So I'm going to talk about something about this active particle. You have been, I think, you already know what is an active particle. Okay. So I'm going to, there are already a couple of talks on this. So I'm going to discuss about a very particular kind of active particle, which is called direction reversing active Brownian motion, and I'm going to describe what is it. And I'll just highlight only some of the features which is different in this model, which you don't see in the other active particle models. Okay. So this is done with my student Ion and collaborator Urna. And okay, these are some of the papers. But this is also part of, we have been working on this active particle for quite some time, and okay, these are some of the collaborators. I think many of them you recognize probably. Yeah. Okay. So although you know, I guess by now what is an active particle, let me, since there are students, so let me start with something very basic, which is just the Brownian motion, simple Brownian motion. And in the active matter community or active particle community, it's also referred to as the passive particle. So we have already heard this term. Okay. So for example, if you take a water drop and then put some colloidal particle or some polystyrene beads. So these are typically of 1 micron size, okay, and then you observe under the microscope. So what you will see is that you see this kind of jittery motion, okay. So if you, for example, observe the trajectory of this particle for a long time, so this is what you will see, okay, just jittery, but it moves, if you look at after a long time, it actually moves a substantial amount, okay. And if you take a, let's say, polystyrene bead of 1 micron, so density is more or less the density of the water for this. And so if you look at the relaxation time, the inner viscous relaxation time, there is a mass of the particle and there is a viscosity. So there is a time scale at which it forgets about its previous velocity. So it forgets the inertia. So this is about 10 to 100 nanoseconds. Okay. So therefore, if you are looking at this particle at a time scale which is more than that, for example, if you are sampling in 1 microsecond or 1 second, so you can forget the inertia of the particle. Okay. So then what? So this is called the overdamp motion, overdamp limit of the Brownian motion. And so if you measure the displacement in a amount of time delta t, so it typically scales like square root of delta t. Okay, it's still a random variable, so every time you measure it, it will be different. So what you can write is the delta xi. So this is the at the ith interval. So this will be square root of 2d delta t times some random number, and this random number is you taken from a Gaussian distribution with mean 0 and variance 1. And this diffusion coefficient is related to the temperature and the friction coefficient of the medium. So to give you a scale, for example, if you again take this silica bead, its size is 1 or 2 micron at room temperature, typically you will see that this typical displacement is of 1 micron in 1 second. Okay. So these numbers are useful to keep in mind. So when I go to the active particle, right? So that's why I showed this slide. Okay. Now, so if you look at a bacteria like E. coli, the size is actually not very different from that colloidal particle I talked about. So if you look at the E. coli, it's 2 micron length, 1 micron width, so it's a rod, but it's of the similar size dimension is basically similar to the colloidal particle I talked in the previous slide. Right? But if you look at this, again you look at under the microscope in the same time scale, so it actually exhibited drastically different motion in that time scale. So what this bacteria does, it has some kind of a orientation, okay, it has a head and a tail, and it moves along the head for substantially some time, okay. So for example, this E. coli usually moves like about 30 micrometer in 1 second before substantially changing its direction, okay. It, of course, it after some time it will change the direction, okay. So this kind of persistent motion, which at this time scale it basically keeps going in one direction, so these are called the active motion in general, okay. So of course after some time it will change direction, and this, okay, how it changes direction depends on what kind of active particle you are looking at, but basically this persistent motion at this short time scale, this is what we will be referring to the active motion. Okay, this is a video we took from somebody's lab in RRI, I think Pramod Pulakar. Okay. So of course you have been, I think, hearing about, or you have seen similar pictures in many talks, that if you put all these particles together, depending on this thing, they show fascinating behaviors. Like for example, this bacterial, some bacterial colony, fish schools, some flock of birds, or sometimes the herd of sheep. It shows these fascinating behaviors. And I think most of the talks in this conference have been focusing on collective behaviors, not only active particle, but in some kind of thing. So I'll depart from this kind of thing. So I will actually pick up only one of those guys, right? So I'll not talk about these guys. Of course, if you put lot of them, they do very fascinating thing, and it's people try to understand this, okay. But what I'm going to do, I'll just pick up one of these guys and trying to understand its dynamics in detail, and trying to convince you, hopefully you'll be convinced at the end of the talk, that although they show these fascinating behaviors at the collective level, even at the single particle levels, they show very unusual behaviors, okay, which you don't see for Brownian particle, okay, like the passive particle. Okay. So again, of course, this, if you look at a ship moving or a bird moving or maybe fish moving, okay, you don't know what the ship is thinking or something, right? Okay, it does something like that. But we are interested in finding a minimal statistical model, okay, which can explain some of the generic behaviors you see in this kind of problem, okay. And a minimal statistical model, as we said, that this active particle at a short time scale, it has a directional motion, okay. So we'll say that this displacement in a small amount of time delta t is proportional to delta t, right? As opposed to, if you remember the Brownian motion, it was proportional to square root of delta t. So here it's proportional to delta t. So it says that at a short time scale, it has some kind of a speed or something like that. Okay. Then, okay, there is a directional vector n hat, and there will be some dynamics for this directional vector. And okay, it will have some stochastic dynamics, and depending on what kind of active particle you look at, this dynamics of this n hat will be different, and then I'll describe some of this. One can of course have a thermal noise depending on the situation. Like for example, okay, if you have a bird, probably okay, you don't care about the thermal noise. But for example, if you have a bacteria, for example, you might have a thermal noise. But it turns out that, again, I showed you the first slide. So if you look at the displacement due to the thermal noise and displacement due to the activity, they are differ by an order of magnitude usually. So most often you can actually ignore this thermal noise. And if you are very adamant saying that I don't want to ignore this thermal noise, okay, go ahead. So what you can do, at least in the free case, or if you put it in a harmonic potential when the system is linear, you can actually write down and solve this problem without the thermal noise. You can solve the problem only the thermal noise, and the full distribution is a convolution of the two systems. Okay. So by not considering the thermal noise, actually you are not missing anything. Okay, you can include the whatever the contribution coming from the thermal noise later by writing down that distribution as a convolution coming from purely this term and purely thermal noise. Okay, so therefore, for most of the talk, I will be not talking about the thermal noise. Okay. So again, okay, many of you are probably familiar of this terminology, but let me anyway walk it to you. So again, the basic models for this active motion. So as I said, the basic model of active motion at this level is basically the model for the unit vector n hat, how it moves, the stochastic dynamics of the unit vector, right? So there are many models, but these two models are often used, and one is called a run and tumble particle, and the other is called the active Brownian particle. Okay. So in the run and tumble particle, the system is in 3 dimensions. For the simplicity, let me just confine to 2 dimensions. It's easier to describe in 2 dimensions. So the n hat, so if it basically changes its direction at a rate gamma. So what it means that, so if you observe your system, let's say you're looking at the system under a microscope after every time delta t. So in a time delta t with a probability gamma delta t, now n hat is in 2 dimensions, it can just define by the angle theta, right? Because the components are just cos theta and sin theta. So theta changes to a new theta prime with this probability gamma delta t, and this theta prime is chosen independently from this 0 to 2 pi within decimal from uniform probability. Okay, so irrespective of whatever the theta you had, you choose independently. Okay, and with the rest of the probability 1 minus gamma delta t, so whatever your orientation, you move by delta x v0 cos theta times delta t. These are the component of the unit vector, whatever the orientation vector, and delta y is v0 sin theta times delta t. Okay, it's very simple. Yeah.
So in the delta t time period, it either changes the direction.
It either changes the direction, so in delta t, either I decide that I change my direction, I don't do anything, I'll just change direction, or whatever direction I had, I'll just move by a small amount. Okay.
In the first model, the properties of the system will be similar to the this freely jointed chain model, right? Because there are segments which are successive segments will be randomly oriented at any angle, right?
So depends on what properties, but some of the properties might be similar to fully jointed, but this length are not fixed length. These length are exponentially distributed. Okay, because the time it runs is exponentially distributed. So length is just velocity
So there is
times the
difference,
time.
right?
So it's like exponentially distributed. Okay. So on the other hand, this in this model active Brownian particle, okay. So in a small amount of time delta t, again the delta x and delta t changes by this amount. This is same as this one, right? It just moves by this amount. But the angle, now it changes continuously, and angle changes by this amount. So angle changes like square root of delta t times some random number, and which is drawn from Gaussian distribution. So therefore, the orientation does a Brownian motion. That's why this term called active Brownian motion. But the displacement does a ballistic motion at this time scale. Okay, and this model, to some extent, seems to successfully describe dynamics of bacteria or artificial microswimmers. Okay.
Excuse me. Previous slide only.
Yeah.
So delta t is just a time in which it's moving in a straight line only, right?
Yeah. For the first case.
Is there like
in
in
the time
first?
it moves in a straight line in both cases. Yeah.
Yes. So in a first model, like is there some time is also particle is taking in turning?
No. So
That is much lesser compared to
so
delta
that's
t.
much lesser. So usually in the actual system, like if you look at a bacteria or something, of course, there is a time which you call the tumbling time, right? Because it has all this flagella, it has to do something. So, there is a time. So, that time is usually smaller than the time it moves, okay? And therefore, in the very basic models, people neglect that time and you say that it turns instantly. But there are generalization of these models where in fact you say that, okay, there is also a time it turns, so in the sense that you just stays there for some time basically, right? So you can actually, you can add all these bells and whistles, and there are models where people actually take into account those things. Yeah. Yeah.
For simulating this model, like you have to consider this delta t to be much less than 1 over gamma.
Delta
Right?
t to be much smaller than 1 over gamma. Yeah. And similarly here, delta t to be much less than 1 over dr basically. Yeah. So this is the dynamics basically in a discrete, right? This is what you do in a simulation, and when you write down, you can of course write down in a continuous time. Yeah. So now, yeah, so this is just to show that, okay, if you look at actually real systems, okay, these are, I think, photographs, these pictures probably you have seen many times. So you look at these things, okay, these are some bacteria, these are wild type E. coli, and you see that this, okay, although there are some little bit of deviation, but this more or less it moves in a straight line and then it changes the direction. Okay, so you can say that, okay, this wild type bacteria to some extent can be described by this run and tumble particle. Okay, on the other hand, this is also some bacteria where you do some mutate some genes. Okay, and then they perform this kind of motion because, okay, there is something problem with the way the flagella moves. Okay, probably it cannot just rotate. And this is more or less what basically you see, or you say that this kind of motion can be described by this active Brownian particle. Okay, and so although, okay, I mean, if you take a particular model, this model will show very different behavior. I mean, like different in the sense that quantitatively these answers for one model will be very different from this one, but there are some generic features, okay? And what are the generic features? For example, if you start with a probability distribution, if you start from the center with orientation equally likely to be in all directions, so you start with a delta function. So at short time scale, they move out ballistically, right? So what you will see is that your distribution will be peaked away from the center. Okay, so this is like distribution, and as time evolves, what will happen that, okay, this particle moves and then they will turn after some time, after some persistent time, and then this concentration will slowly pick up near the center. Okay, this is, you can call it a artist impression or something like that. And then suddenly, okay, slowly this peak will grow and the whatever the weight at the boundary will decrease. Okay, and okay, so this is what it will look like, and this is at the scale of delta t. You will still have some boundary because there's still some probability that this particle still keep going in one direction. Okay, but eventually, if you look at a scale of square root of delta t, so what you expect that it will have a Gaussian distribution at that scale. That's because if you this particle, okay, although at small short time scale is going there, after some time it will just turn, etc. And then this central limit theorem will tell you that, okay, at a very large time scale, basically it should give you a Gaussian distribution if you look at a scale of square root of delta t. Okay, and this is a generic features you see in all these active particle models. Okay, and of course, if you, okay, the exact shape will be different if you take, for example, model A versus model B. Okay, but more or less it will be something like that. Similarly, the stationary state, okay, so if you put a particle in a potential, you expect that it should reach a steady state. And again, it's useful to compare with what we call this passive particle, right? Because we know that what is the stationary state of a Brownian particle if I put it in a potential, right? It's an equilibrium distribution, and it's if I have a Brownian particle in some potential u, so it reaches this equilibrium distribution which is given by Gibbs-Boltzmann distribution, right, exponential of minus beta u, okay, divided by the partition function. So for example, if your confining potential is like that, so which is a minimum at the center, so you expect that, okay, your distribution would be basically okay, more or less like the invert of the distribution, right? Okay. So this is whatever your Boltzmann distribution or Gibbs distribution. But for active particle, okay, you see something quite interesting. So it has two phases. So depending on the persistent time. So again, if you remember, the persistent time is the time at which the particle basically more or less moves in the same direction. The change of the direction is not substantial. That's the persistence time. And if the persistence time is much smaller than the relaxation time of the trap, if you have a trap, then there is a relaxation time, right? And then you have a distribution which looks like a passive, basically, which will more or less look like a distribution of a Brownian motion. But on the other hand, if your persistence time is large, so it keeps going in one direction for a long time compared to the relaxation time of the trap. So what you see is that your distribution is actually quite different. So it's actually, it's crowded away from the center, right? So this one is very different from this distribution, okay? So this is called the active phase, okay? And it's basically what you see is that in the passive phase, okay, you have frequent turning of these trajectories, so this looks something like that. But in the active phase, okay, you basically go there and more or less it just stuck at some point, okay? And then it decides to move again, it goes in that direction and stuck in there. So this is what basically trajectories looks in the active phase. Okay. So for example, you can actually, yeah. Like for example, if you have a particle, for example, Brownian particle in a harmonic potential, right? There's a K and there's a gamma. So at some point, the particle will relax. For example, you can ask, like, okay, if I have a time particle there, how long does it take to come to the origin? Or something like that, right? There's some relaxation time, right?
Persistence time will affect that, right?
Persistence time will not affect that because persistence time is, it's connected to the whatever the active motion. There is two time scale, right? One is the relaxation time, that's irrespective of whether you have a active motion or a passive motion, okay? Just the relaxation time, if you have a trap, there is a relaxation time associated with the trap. For example, if you have a stronger trap, okay, or versus a weaker trap, right? So this time will probably go like 1/k, right?
So that trap property.
It is the trap property. The relaxation time is the property of the trap, and the persistent time is the property of the active agent, basically. So these are two independent, and depending on this time scale, you have to. So in, yeah. This one, z-axis is distribution. P of xy, it is a 2D distribution. So if you look at the, so you just think of this guy, this is in one direction, you rotate it, right? So like for example, instead of one direction, if you look at a harmonic trap in two direction, right? So this is what it is basically, this is, yeah. It's a characteristic time. It's, for example, if you have a RTP, it will be 1/gamma, right? Because gamma is the flip rate, right? So 1/gamma will be the persistent time, right? So this is a characteristic time basically at which it, after which it changes the direction substantially. Like for example, ABP, it will be 1/dr, right? Okay. So now, so in fact, one can actually compute the phase diagram for, you can take some model and actually you can go ahead and do this phase diagram. This is not only qualitative, what I have shown. And you see indeed that, okay, for example, if you take this model, okay, this is what we did with our collaborators at some point. that, okay, if you take this model, okay, dx dy equal to this minus gradient of the force plus V0 times sigma t, and sigma t is just, now it is in 1D, so it is only plus and minus. Basically, it just either this way or that way, right? So this noise is called the telegraphic noise or dichotomous noise, and this flat portion or these portions are basically distributed exponentially. Okay. So if you take this model, okay, if you, it has two parameters alpha and p, and depending on the value of the alpha and p, actually you see that, okay, there's a phase diagram and you have a passive phase and active phase, and passive phase is basically characterized by when the probability distribution goes to 0 at the boundary. Okay, don't pay too much attention what is happening at the central part. Okay, so passive phase is the one where the probability distribution decays to 0. On the other hand, active phase is the one where the population increases at the boundary. Okay, you see this this thing. Okay, and then you can also look at, for example, harmonic potential. Depending on the activity, you can see that, okay, the shape changes from the passive to the active depending on your activity parameter. Okay, changing activity means basically just changing the persistent time. Okay, similarly, you can see it in higher values of p. There is no boundary. So because there is no thermal noise, right? So you have this motion dx dt equal to force plus something, right? So at some point this term will balance this one. So there will be a turning point, right? Except in one dimension, except for p equal to 1. So they are, and p less than 1, they are, okay, this is slightly different. But like say p greater than 1, there will be a turning point after which basically this force, trapping force and this force, they will balance, and that will set the boundary condition that the particle cannot go beyond that. It will basically see this particle, this is like a constant force, right? This is a over the motion, this is a constant. Let's say put sigma equal to 1, it's going in outer direction. This is a constant. This force increases with x, right? At some point this force and this force will balance, and the total force is 0 at that point. Then the velocity will be 0, and then particle cannot move. Then, okay, the particle is stuck there. At some point it decides to turn. Of course, then this sign will be negative, and then particle just moves in the other direction. So it sets the boundary by itself, basically. Yeah. But of course, if you put a thermal noise on top of it, it will not be like a sharp boundary. It will be, okay.
Sanjib, so the passive phase is defined by the probability that probability will be 0.
Probability goes to 0
at the boundary.
Yeah, exactly.
But it can have a complicated shape also.
It can have a complicated shape also, actually. Yeah. Like as you see that here, it actually has sometimes complicated shape, actually.
Okay.
So basically, in some sense, if you scale it, you have to scale it properly. You say that the tail is Boltzmann-like, basically. The tail of the distribution is Boltzmann-like. But of course, you have to scale it properly because it's it stops at some finite this thing, right? So yeah. This is the same one with p equal to 3/2. This is the potential. This is p equal to 3/2. This is p equal to 4. This is p equal to 2. Yeah. So yeah. So this is basically active and passive are distinguishes by this, just that distribution whether it population goes to I mean, yeah, it goes to infinity or 0.
What is sigma in the previous? What is sigma in the?
Sigma is the, see, you can just think of sigma is just your unit vector, right? Earlier you have this n hat, okay? But one direction unit vector either this way or that way, right? So it's just +1 or -1. So therefore this is usually called the dichotomous noise. So it basically flips between +1 and -1 with a rate gamma. So now even the relaxation is quite unusual. Again, it's useful to compare with passive particle. So you know that passive particle relaxation is very simple actually, right? Because, okay, if you have a potential, okay, there is a, if you look at the Fokker-Planck equation, okay, there's an operator, Fokker-Planck operator, it has some eigenvalues, okay. And if you write down the distribution, it will be, okay, some equilibrium, and this lambda 1, lambda 2, lambda 3, these are just eigenvalues, right, or minus lambda. The lowest or highest eigenvalue is 0, that's why you have this equilibrium state. And then, okay, these are the corresponding eigenfunctions, left and right eigenfunctions. So now, so basically if you look at the deviation from the equilibrium at long time, how does the probability distribution deviate from the equilibrium distribution long time? So this goes down exponentially, so exponential minus lambda 0 t, and this lambda 0 depends on whether your starting point is, you start from the center, it's a symmetric potential, let's say, or somewhere else. So for example, if you start with somewhere else, so you have a finite mean, so then this lambda 1 gives you the whatever the relaxation time 1 by lambda 1. On the other hand, if you start with the from the center origin x equal to x0 equal to 0, then this lambda 2 gives you the 1 by lambda 2 gives you the relaxation scale, right? But this is very simple, this model, right? And so for example, if you take a harmonic potential, lambda 1 is mu and lambda 2 is 2 mu. But again, for active particle, even the relaxation can be quite interesting, as you see it here. So if you look at the relaxation now, it is lambda 0. So if you look at, okay, this is in a harmonic potential. So if you look at x0 not equal to 0, okay, it's more or less like the passive particle, the relaxation is. But if you start with the origin, so now that it's given by the variance, okay, I mean, you can characterize the relaxation by the variance, okay, and you see that this lambda 0 has this thing that, okay, it's basically given by minimum of this mu plus 2 gamma d. So initially it actually changes with gamma, gamma is the activity parameter, and then finally it fixes to the passive limit, because gamma going to infinity is the passive limit, right? But you see actually this unusual relaxation for the active particle, okay? And here you see that actually for mu equal to 2, you see that for different values of gamma, actually you see that, okay, one is here somewhere and one is somewhere here. So this is like the passive one, because this is like a 2 mu, mu equal to 2. But on the other hand, here for is 0.5, you see that this is 3. So it is actually the relaxation can be very different for this kind of problem. Okay. So now enough of this active particle. So with single time scale, so far what we have talked about this active particle having single time scale, right? Either you flip with a time scale, or you have this direction you changes, but there is a time scale 1 over dr. But what happens, suppose you have an active particle with multiple time scales, and you do see actually systems where this active particle is multiple time scale. For example, this is this organism. So this is a large compared to bacteria, E. coli, and also it moves actually quite slowly, but this is something usually these experimentalists do. Because it moves quite slowly, then okay, you just make it fast. So it's not actually they don't move at this speed actually, okay? It's I think maybe 10 or sometimes, yeah. So what you see is that basically, okay, they more or less do a active Brownian particle kind of motion, but suddenly they decide to change the direction completely, okay. So they are like this innocent active Brownian particle, and then suddenly, okay, something occurs and it just changes the direction, okay. And again, it does active Brownian motion. This is again some another microorganism, and then there are, okay, some various organism. You see that they have this sudden directional reversal, okay. You can in fact also prepare these systems artificially. There's something with titanium dioxide coated on one side, gold on another side, and depending on which color light you shine on them, it either moves in this direction or the other direction. And during the movement, it of course does whatever like this active Brownian particle kind of thing, okay. And you see that if you don't shine any light, it of course moves like a Brownian motion. Okay. So depending on the light you shine, it basically changes the direction. It basically one side, either the gold side or the titanium dioxide side, it becomes active basically. So the minimal model to describe this kind of motion is what we call it this direction reversing active Brownian particle. So now on top of this active Brownian particle, this was the model. If sigma was 1, this was your active Brownian particle model. Now you have this dichotomous noise sigma which takes value plus minus 1, and the sigma changes to minus sigma. Basically, if it was in plus 1, it will go to minus 1 with a probability gamma delta t in a small amount of time delta t. So with a rate basically gamma, it changes the direction. So you see that basically, okay, if you look at the trajectory, this guy is moving like a active Brownian particle, and then suddenly it changed the direction, and that this, you can think of it like some spin or something, okay, depending on, okay, this state variable can be either blue or red basically. Okay, what happened to this? I can't see anything now. I think I have infinite time, I think now. I think it's dead. This one is, okay. So now, so you want to study this particle, again a free particle, what is the probability distribution? And okay, before looking at the probability distribution analytically, one of the easiest way to actually visually look at the probability distribution is take lot of particle, and these are independent, don't put any interaction among these particle, and let them do its own dynamics. Okay, so you basically start everything from a state blue. So blue and red defines the state of the sigma. So you start all particles orienting this way, but each particle has its own dynamics, right? So their trajectories will be different. And then if you evolve them and they don't talk to each other, so the density will be basically like the probability density for a single particle, right? If you normalize it. So this is how they evolve. This is the case where this flipping rate is more than the your dr. On the other hand, this is the case where flipping rate is less than your dr. And you see that these two evolution, they are quite different, right? Of course, initial is more or less same. They have some kind of everything goes there. But you see that this very fast it becomes isotropic, right? But on the other hand, this anisotropic persists for a very long time, and then eventually it becomes isotropic. Okay, so this case is, I mean, we actually looked at analytically in both the models, and okay, so maybe let's both the cases, all these cases, and okay, this is what basically.
The time difference was just order 1, right, in both cases?
No. So this is the one where, this is the case where this flipping rate is less than your turning rate.
Correct.
On the other hand, it's the other way. It flips more but turns less.
Both become homogeneous almost same time.
It will become homogeneous at the same time. Right? Time is, I mean, depends on when you say same time. These times are determined by these things, gamma and dr. You can choose gamma and dr so that they can become homogeneous at the same time. But this basically time scale is determined by this gamma and dr. Okay? So it's not the same time, but in terms of gamma and dr, it is the same time basically. Yeah. So now, so basically, okay, so there is a initial phase. As you see, there is an initial phase, and in initial phase, as I said that in the generic peak size, that okay, there is a peak at the boundary because this peak corresponds to the particles which didn't flip at all. It just keeps going in direction that contributes to the peak. And then there is a flat region, and the flat regions are contributed by this particle going there, but few flips. Okay, that contributes to the flat region, and this is more or less same in this. So there is the early time regime where this time scale is much smaller than both the time scale. So this is a generic regime which you, okay, the analytical expression of the probability distribution in this regime will be probably different from, it is different from, let's say, active Brownian particle or the RTP, okay, which we have in the paper, but okay. But generically, it has a similar behavior. If you remember this, whatever artist impression picture, right? Final is again, it's Gaussian, generically similar to all active particles. So in this case, what happens that this is the case where it very fast becomes isotropic. This is the second case. This is also actually similar to this one, but this case is very particular. And in this talk, basically, I'm going to focus on only this one, and this is the intermediate phase where you see some novel features for this model, which is absent in other active Brownian particle models. Okay. So for example, okay, you can also look at the survival probability. Okay, it goes power law, it has two exponent, but okay. But okay. So for the time being, okay, let me just focus on this model. Okay. So this is this intermediate state. So basically where your time scale is much larger than this gamma inverse. Gamma inverse is the flipping, sigma goes to minus sigma. And but much smaller than the dr inverse. This is the case where this guy is basically moving very slowly, right? Dr inverse is the ABP time scale. In this case, you have this anisotropic. Now, if you look at these two directions, you have this one direction, this perpendicular direction. So this direction is okay. I mean, it's you get something, but okay, it's not so interesting. But this perpendicular direction shows something very interesting. So it's basically you look at the particle which was initially in this direction, right, and then it moving. So you look at the position fluctuation in the perpendicular direction, this component, and this component shows something very interesting. Okay. So in a mathematically, okay, this in this range, okay, this motion, this perpendicular fluctuation can be modeled by something. Okay, so if you look at a dx dt equal to eta, it's like a Brownian motion. But now you have a phi, you can think of like a diffusion coefficient or diffusion coefficient square. And this phi again performs a Brownian motion. So you can think of it like, okay, you have Brownian motions, which diffusion coefficient itself is has a stochastic dynamics. Okay, and you can go ahead and solve this thing for the probability distribution, and you see that this perpendicular direction, you have a ballistic fluctuations, right? So this orientation is still diffuse, this fluctuation is still diffuse, but this fluctuation is the ballistic. And so basically a ballistic means basically the x perpendicular goes like t, and you can actually scale this distribution, and this scaling function has a very nice looking form. It's a very, okay, this form. And okay, if you look at the tail, it has an exponential tail basically, right? And this is something, this is what something I wanted to convince you that even for a single boring active particle, you might actually look at some properties which you will find something very interesting. Okay, okay, I'll probably just skip the calculation. I can tell you later. We can also look at the survival probability. Survival probability is basically saying that, okay, if I have a target or if I have some first passage time, for example, if I have a target and if I start from somewhere, how long does it take to reach the target? Okay, that's called the first passage time. And it's, of course, it will be a random variable, and what is the distribution of this. And you can again calculate the first passage time distribution, and again it has some, okay, it has some exact distribution basically. But let me not spend time on this. Okay, so this is what you see basically that, okay, so this is what I wanted to show, that it has this 1/t behavior. Okay, so if you remember for the survival probability for Brownian motion, it goes like 1/square root of t, right? So it's error. So for the Brownian motion, if you have a Brownian particle, you start from some x0 and you ask what is the probability that till time t it doesn't hit the origin. So this is the survival probability s of t given x0. So this is given by error function x0 divided by square root of 4 dt. So this see that, okay, this for large t this argument becomes small. So therefore this goes like 1/square root of t for large time. Okay. Okay. So as opposed to square root of t, now you see that this goes like 1 over t. So this is the reason I want to show this 1 over t is. Okay. So now, okay. Okay, so this is, it depends on how much time I have. Probably I don't have much time. How much time do I have? Huh? 10 minutes. Okay, so yeah. So maybe let me just spend 5 minutes on this one. Let me see if I can spend 5 minutes. So I've said that, okay, for any active particle motion, the final distribution is Gaussian. And that I said that based on, because if you take any random motion with a finite time scale, right? So usually what happens, there's a characteristic finite time scale, tau, let's say. After tau, these motions becomes uncorrelated, right? So then you know that if you add uncorrelated random variable, independent random variable, their sum is a Gaussian. So that is the reason you expect Gaussian distribution for the very late time, because your full displacement is sum of the displacement at different times, and you can choose these times long enough so that they become. But this is an heuristic argument. It's not a rigorous derivation, right? I mean, I think most physicists will be happy with this kind of heuristic, but we want to do something better. Yeah.
If there is bias, the distribution won't be Gaussian.
If there is bias, then the distribution, depending on what kind of bias, if you put a constant force, so you can have a bias, it can still be Gaussian, but the center of the Gaussian can move with a speed.
But it is changing its direction after certain amount of time, right?
It is.
Activity. So there will be two directions and like opposite flipping. So it will be like,
So as long as it is symmetric, your bias is with the distinct. See, there is a persistent time, right? Till that time, whatever your dynamics, I decide to go in one direction. And then I change my direction. But this persistence time is some, let's say, 1 microsecond. And I observe after 10 minutes, right? I can break the time as 1 second. In 1 second, I have done many flips. Whatever I have done, many flips, right? Okay. As long as there is no overall drift, okay, it is still symmetric. And this time, whatever I have done in first 1 second, next 1 second, these are uncorrelated. So therefore, the displacement in first 1 second, displacement in second 1 second, third 1 second, these are uncorrelated displacement, uncorrelated random variable. And if I add them, their distribution will be Gaussian by central limit theorem. But these are of course not exactly uncorrelated. That's why I said that it's a heuristic argument. But we can do something better. Okay. So what we did is actually, so you can actually look at, so any active particle, if you look at it, it has a generic, this is a generic model because r dot equal to v, right? This is your self-propulsion velocity over damped motion, r dot equal to v. And okay, for example, suppose you want to look at only one component, E of x bt, x is just the projection in the x direction. And okay, this v is, this v is the projection of the vector v in x direction. You can write down a Fokker-Planck equation. You can of course do it for both x and y, but let's keep things simpler. Okay, so this will left side is basically is given by just the your pure advection, right? It is del del t times v times del del x of this thing. Okay, because you have a v, it's advex. Okay, then there will be a operator which will depend on the dynamics of v. Right? This is where in the Fokker-Planck operator, the dynamics of v or the dynamics of your unit vector comes in. And of course, this operator will be different for different models, right? For example, this model I just talked about. So there will be a term like diffusion like term in the theta variable because of this theta is changing. Also, there will be a term because your sigma variable itself is changing. But for example, if you take a normal RTP, this term will not be there, only this term will be there. Or if you take a normal ABP, this term will not be there, this term will be there. But if you take some any other active particle model, it will be something different. Okay, but you can generically you can write down a Fokker-Planck equation, and what we are going to assume is that this n dynamics, unit vector dynamics, v dynamics, it equilibrates or it goes to a steady state. It need not be equilibrium state. It has a steady state. And this is what you expect, right? Your unit, whatever your orientation vector, whatever it is, either it flips back and forth or your orientation changes, but your theta variable is between 0 and 2 pi, it will equilibrate, right? So this P of Vt, which is only the distribution of the V, the self-propelled velocity, it has a steady state. So it means that P of Vt you can actually expand in the eigenbasis of this operator L, right? So it will have eigenvalues and eigenfunctions, okay? So therefore the joint distribution P of x Vt, so now it's a it has x, v and t, but you can just think of it like a P of just v and x and t are some parameters. And you know that if you have an eigenbasis, any function you can expand in that basis, right? That's why we use this eigenbasis. So therefore, P of xt, you can expand in this basis of v, but of course the coefficient will be a function of x and t now, right? And if you want to write down the position distribution, which is what we are finally interested in, so this is just the integral of this object over v, and you know that this, since these are eigenvectors, the zeroth eigenvector, the integral will give me 1, right? Because this distribution finally approaches psi 0. So therefore, it has to be normalized. It has to give me 1. And for all other psi n, where n is not equal to 0, it has to, the integral has to be 0, right? So therefore, it is given by that. And then, okay, you can just do this calculation, and basically the take home message is that this rho of xt, which is just the your distribution of the position, so you can write down in this perturbation series in this tau 0, which is your activity persistent time, but of course you need a, by itself it is not enough, so it's tau 0 by t. Right? Tau 0 by d is a small parameter. And what we can show is that at the zeroth order, it satisfies the diffusion equation. And this is this diffusion equation which gives you this eventual Gaussian distribution. And in fact, you can actually find out the correction to that. And interestingly, even the correction terms satisfy this inhomogeneous diffusion equation, and whereas the source terms depends on the solution of the previous diffusion equation. Okay, and you can of course okay, find out there, and you can write down the full distribution. Okay, whatever is generically there. Okay, so this is just to show that okay, it works. And for example, this whatever this direction reversing. So this is the eventual Gaussian, but actually you can look at the correction by subtracting the Gaussian, and you see that this is the first mode. Okay, this is the second one, this is the third one, and so on. And this coefficient you can in fact compute explicitly. Okay. So now, I have about 2 minutes, right? Okay. So, okay. So now again, I want to see, this is, so far it's just a free direction reversing Brownian particle. Now I want to see what happens if I put it in a trap, right? You saw that even for a active particle with single time scale actually shows very different behavior. It has a transition from an active to passive phase, right? So now, of course, you have one more time scale, and does it give anything extra? Okay, and okay, maybe okay, this one let me just skip this one, and let me just go to this one. Okay, let me just skip the mathematics and do that. Okay, so what you find is that now you have 4 phases. You had this all 2 phases, passive and active. Now, since we have force, we rename this passive 1 and active 1. Okay, these are similar to the whatever the phases you have seen before. There is either a crowding at the boundary or crowding at the center. Right? These are the typical active and passive phases. But on top of that, now you have 2 more phases, where both in the active phase and a passive phase, there is a divergence at the center, and this divergence, so there is basically a divergence at the center. Okay, and this divergence is because in this time scale, all these trajectories, because this is a time scale where flipping occurs at a large distance, and all the trajectories goes through the center. Okay, and in fact, this is the divergence. I think I was giving a talk and somebody mentioned that. I think there's this drawing thing where you have this scale and where you can just pencil goes back and forth and you can change the direction, right? So this, I don't know what is it called, something, right? It just goes back and forth and you slowly change the direction. So what will happen is that after some time the center will tear, and this is the tearing divergence at the center of the paper basically.
What's the nature of the divergence?
What is the nature of the divergence? And that's very interesting. So, see, this nature of the divergence is basically, okay, so why is the divergence occurring? Okay, so let me just qualitatively say, because this is a time scale where theta is changing very slowly, right? So you can actually write down the Fokker-Planck equation. Okay, this is the full Fokker-Planck equation, but now this is not a good way to look at it, because in one direction things are changing very fast. So what you can do, and you see that as you see that the theta changes very slowly because the epsilon parameter is basically very small, right? So you can go to a basis where you basically look at the perpendicular and the parallel direction of the instantaneous theta, because theta changes very slowly, and you see that then this part of the equation or whatever, this part of the term decoupled from there, right? Because this part doesn't depend anything on this one. So this is actually two independent motion in that scale, right? So this motion along the theta and the perpendicular is very different, and perpendicular motion is very simple. It's just the overlay motion of a particle without any noise. So it just quickly comes to the center, and the other motion is like a RTP, run and tumble particle, one-dimensional run and tumble particle on that direction. So you are doing this one-dimensional run and tumble particle, and then somebody is changing the direction very slowly, right? So then, and okay, you know the distribution of this run and tumble. This is what we did at some point, and it was also actually known in some this thing. So you actually know the steady state of the one-dimensional run and tumble particle, and as I said, that the other direction is very simple, just becomes a delta function, and then you can actually write down the full distribution, and this is what your parallel distribution is. And okay, this is the parallel distribution, this thing. The full distribution is basically this one, then you integrate over theta, and this is what your full distribution. And this divergence is basically this square root of 1 by z1 square, z2 square. This z1, z2 are just a scale, this thing. So this is the square root divergence at the center. And if you look at the only one projection, this square root gives you a logarithmic divergence. So if you just project in one direction, so you see that, okay, this is what, okay, this is what your, actually this is what your equation is. And then, okay, this guy basically gives you, this divergence is logarithmic if you look at the marginal listing. Okay, so you can actually, in fact, compute this function properly. This is called this hypergeometric function. And, okay. So in fact, you see this thing now, this is the passive phase, right? For this model, in some parameters, it becomes a passive phase. So even in passive phase, you see that, okay, there's this scaling function, you see that near the origin, it has a logarithmic divergence, but of course, tail is Boltzmann. So you have a Boltzmann tail, but there is a logarithmic divergence at the center. Okay. So both the active and the passive phase are accompanied by this logarithmic divergence. So in fact, one can, in fact, okay, go ahead and look at all the phases, and in some cases, actually limiting cases, you can find it analytically. So basically, these planes you can find it analytically. So you have three parameter dr, gamma, and mu inverse. Mu is the trap strength. Okay, and then you can construct some kind of a phase diagram which separates the active and the passive phases. And okay, these things you can, that 3 planes, you can do it analytically, and then okay, you can do some simulation, and okay, you can see that okay, this matches basically. Okay. So summary is basically okay. So okay, whatever I have written it here, but basically what I'm saying is that okay, this direction reversing active Brownian particle, and Paul is not specific to direction reversing active Brownian particle, but any active particle which you have 2 time scale. Okay, you may expect to see some very novel features, interesting features, where these 2 time scales interplay basically. So you should look at the interplay between these 2 time scales, and if you observe that, you will see some features which are absent in normal active Brownian market. Okay, so he has this okay both these dynamical phases, 4 dynamical phases, and also in the case of trap, you have this phase diagram. So I think the take home message is whatever I have said. Okay, I mean I've talked 1 hour, but I think this is what you should remember basically. Okay, so apart from that, there is another take home message is that I hope I have been able to convince you that even at a single particle level, which might sound boring, okay, why do you want to just look at one? You will actually find very interesting behaviors. If you know where to look at basically. And then the other thing is basically if you have active particles having multiple time scales, can exhibit very interesting novel features which you will not see or you would not have seen in the normal active particle motion. Yeah. So thank you for your attention.
Question?
About, have you done any large deviation analysis, and have you found?
We have done large deviation analysis, and you can see actually there, again the large deviation tail depends on okay which model you look at it, but we have looked at the large deviation this thing actually.
Yeah. So you said your inspiration was to model these head-tail reversing bacteria.
Yeah,
And we saw a very nice movie in which these bacteria assembled in some channels, and they were able to retrace the channels.
Yeah.
So I guess just the simple head-tail reversing move would not be able to capture that, because suppose you're moving in a curve and you just reverse the head-tail, you'll move along a tangent.
So no, they can actually reverse. This is like this train with 2 engines on the 2 sides.
Okay.
So this guy can actually go back like this. This junction. No, sometimes you put this train with 2 engines, right? It goes there and then immediately it changes there. So it can either go this way or that way. It doesn't actually change the.
It was retracing the curve, retracing the path in which.
So now, okay, so
it cannot capture using this, right?
Yeah, so actually this is something I didn't want to mention, but you are okay. So actually, I don't know whether you have asked me the same. So this thing, right? And the first one, right? Yeah. So actually, let me just see where's my. This one, right? Yeah. So this one actually. So this model, okay. So other guy, this other one probably is more close to the model I have described. But this model, okay, this actually it was noticed before. So this actually they leave a slimy track. This thing. So actually they retrace the track. So this active, whatever this direction reversing active Brownian particle is not exactly the model for this one, but one can say that okay, it's motivated by this one. But for example, for this one, Pseudomonas putida, Paul is described better by this active Brownian. Yeah. So this one, yeah. So if you notice it closely, this actually retraces the path. Yeah. Yeah.
Yeah, so for the run and tumble particle, right? So you showed that the relaxation depends on the initial condition, right?
So this is the one where the initial orientation is chosen uniformly.
So if you have, okay, so in that is the reason probability is not.
Yeah, but see, but the point is that that initial condition dependence was the boring dependence, right? Because it didn't have much information. The one where you choose from x equal to 0, where it is given by the variance, so that had the more interesting behavior, right? I think, let me just I think 1 minute. Previously, this one, right? Yeah. See, if you notice this one, this, see, initial condition dependence was here when x0 is not equal to 0, right? But in this case, this behavior was always mu, that time scale is always 1 by mu square, irrespective of gamma, because it's just basically relaxing to the center of the potential, right? So that's not very different from what you see in a passive particle, because they are also, if you have a particle away from the center, the lambda 1 or 1 by lambda 1 is the trivial time scale, it relaxes to the origin. So it doesn't have any interesting information about the noise, right? So the interesting information about the noise is there in the variance, right? So it's basically the second eigenvalue, right? And the second eigenvalue is, you keep everything symmetric, x0 equal to 0, so it's symmetric about x0. Your initial orientation is symmetric, and then that captures the whatever the information about the noise, and that has this unusual relaxation which is not there for your Brownian particle. So similarly, if you take some sigma, you will have something which will be just a relaxation of the sigma, right? So that's again a not very this thing. So you want to see something interesting which will be basically coming because of this active noise. Yeah. Yeah.
I can ask another question. So also like here, there is a force balance, and because of that, there is a natural boundary condition which is coming, right? So if I really put the bacteria or whatever in a boundary, right? So I should put the boundary within that like sort of virtual boundary being set by the dynamics, right? Otherwise, the bacteria will never see the confinement.
No, no, I didn't see. There is a boundary of the cell where you keep the bacteria. You are not talking about that boundary,
Yeah,
right?
now I'm saying that let's put that boundary.
Okay.
And you already showed that there is a natural.
That boundary is infinity.
But let's say that we can put it, right? Because when we look into the first passage properties,
yeah, but
that's a finite boundary we put.
So that then is a different question you are asking, right? How long the bacteria takes to go from here to some boundary,
right?
Right? So you can ask, if you put another boundary, of course the bacteria cannot go outside that boundary, right? Then it will be trapped by that boundary, right? If you put a boundary, hard boundary, within that, no, I think I understood what you are asking. Yeah. So for example, if you put a hard boundary, which is where you are keeping the bacteria, which is smaller than this boundary, of course, then the bacteria cannot go out of there, but it will be still trapped by the boundary, and the distribution will be still populated around the boundary. So this boundary is set by the trap. There's no boundary here, but if you put a physical boundary, that's a trap with a infinite potential at that point, right? That modifies this potential. Putting a box is like a boundary, no? It's like where you have Gaussian, or let's say quadratic, and then it's an infinite potential. That you just modify the potential. So irrespective of whatever potential you put, it will set the boundary condition, right? So that boundary condition will correspond to that potential, basically. Yeah.
Sanjib, you showed this distribution of the particle displacement is like exponential sometimes.
In other system, in passive system as well, when you have disorder, you see similar type of distribution at very short time scale. So there, this disorder is very important, and diffusivity becomes exponential or something like that. Is it not what leads to this exponential distribution in this case?
So this exponential distribution basically leads to that. Okay, so if you have a disordered system where diffusivity itself varies with time, like for example, you can think of it like a for example, okay. So I'm a theorist, so I can speculate. So for example, you can think of it like a medium where you are adding and subtracting heat, right? Like temperature is going your delta T is some plus minus some noise, right? So on the average, the temperature is 0, but of course temperature will increase, right? You know that delta T square will go like time, okay? So suppose you have a system medium where you are fluctuating the temperature, and you are assuming that, okay, this temperature fluctuation doesn't set up any convection, etc. in the system, but this only changes the diffusivity, okay? So this will be a model where your actually no, yeah. So this will be because the T will be your sum over delta Ti, right? Like this, Ti is just the temperature changing with time, right? And this is the total temperature at time T will be just a fluctuation of the temperature. You're just adding temperature, either adding or this thing, right? So this will be in some sense like a medium where your diffusion coefficient does some kind of random walk, basically, right? And in this kind of systems, if you say that this is a disordered system, we'll show this exponential tail, basically.
But here it's different, right?
It is similar because if you look at the equation level, okay, so this is the one can actually show that this is the effective equation at this scale, and you see. So in fact, these things are coming from because you are looking at the perpendicular component. This noise eta is coming from this direction changing very fast. So at some thing, it basically approaches like a Gaussian noise. On the other hand, this one is like the orientation, which changes very slow, and then orientation is a Brownian motion. Okay, and so this one you can think of it like this is a Brownian motion, but with a diffusion coefficient, which itself is a Brownian motion, basically. Okay. And it's in that sense, it's the similar mechanism where and you actually see that then now, see this gives you a square root of T, but then on top of that you have a square root of T there, right, when you integrate, and that gives you this time, basically. So that gives the T time scale.
So let us thank the speaker.